Okay, I think I could go ahead with my introduction as people are still joining us. So hi everyone, welcome to the Essex Seminar Series. My name is Kazi, I'm your moderator today. I'm very excited to announce our speaker, Professor Alan Robinson, who is joining us from Colorado State University. So he's going to talk to us about how we don't all breathe the same air. At the end of the talk, we're going to have a Q&A session where I encourage everyone to unmute themselves and ask questions. You can raise your hand, you can type it in the chat. This talk is also recorded. It will also be posted on our YouTube channel by the end of the week. So a couple words about our speaker. Dr. Alan L. Robinson is a professor of mechanical engineering and a professor of atmospheric science at Colorado State University, where he serves as dean of the Walter Scott Junior College of Engineering. His research focuses on the impact of emissions from energy systems and other sources on air quality, climate, and human health. He is a fellow of the American Geophysical Union and American Association for Aerosol Research. Without further ado, please go ahead with your presentation, Dr. Robinson.
All right, thanks, Cassie. Can everybody hear me? I'm coming through? Okay, perfect. All right. Well, thanks for the introduction. I'm going to be talking about some of my work, thinking about human exposure and environmental justice. So we don't all breathe the same air. Let me get my screen to advance here. Perfect. So really,
you are not sharing. I think you stopped sharing. Since
I stopped sharing. Hold on. Perfect. How about now?
Now we got it. Thank you.
Perfect. All right. Well, I'll show my first slide again. Anyways, there's my intro slide. We don't all breathe the same air. And so really, I've been interested in the last decade. I've spent a bunch of times working on human exposure, linking the public health studies. But in the last 5 years, we've been thinking a little more about exposure disparities, environmental justice. And this, of course, is a topic of a lot of interest. And, the picture here is EPA announcing a new office for environmental justice. And I just pulled off the EPA website, their definition of environmental justice. Environmental justice is the fair treatment and meaningful involvement of all people, regardless of race, color, national origin, or income, with respect to the development, implementation, and enforcement of environmental laws, regulations, and policies. And this goal will be achieved when everyone enjoys the same degree of protection from environmental hazards and health hazards, and equal access to decision-making to have a healthy environment in which to live, learn, and work. So a lot of words, but that's what we're sort of thinking about. And we're really thinking about the first one in this talk, really about the degree of protection from environmental hazard or differences in exposures for different communities. And so this is another way to sort of think about it. They talked about in that EPA definition, outcome and process. So we're going to be talking more about on the outcome side or the exposure side. There's another dimension you can think about environmental justice is, a local dimension. There's a local steel mill and what kind of impact that's having versus sort of more systemic impact and what occurs across the country. So in this talk, we'll be really thinking about exposures, so more on the outcome end, and we'll be thinking about it at a national context, what's occurring across the nation. So we're going to be thinking about it more from a systematic perspective or systemic perspective. So we're going to be operating, this talk really is going to be sort of in the upper right-hand corner of this diagram here where we're talking about. We won't be talking about process and making sure that everybody is involved in decision-making and things like that. That's also really important, but that's just not my area of expertise. And let me see if we're sort of combining, information. So how does these exposure disparities or environmental injustice occur? Well, you've got, a map of air pollution exposures. That's what's shown on the left. And so this is a national map that we've developed from some of our work of cooking and traffic primary PM 2.5 concentration estimates. And these are at the census block level. So, within a city, it's literally the spatial resolution is about a city block. And then you couple that with distributions of population, demographic characteristics of population. That's what's shown on the figure on the right. And the color scale is showing the fraction of people of color. And you can see that, the demographics were not distributed uniformly. We're not a homogeneous country. In the Southeast and parts of California, there's a larger fraction of people of color. So what gives rise to environmental injustice when these two diagrams come together and you have differences in pollutant concentrations basically correlated with differences in population demographics. And so that's what we're going to be looking at. In my work, really focus on the left-hand side of the diagram, developing these types of maps, but we combine them with the census data to look at these questions. So you can then blow this up. So this is the Pittsburgh MSA. So this is Western Pennsylvania, where I was on the faculty at Carnegie Mellon for 25 years. So a lot of my research was focused on Western Pennsylvania. And again, on the left is the same map that we looked at before. And the center, this is the MSA. So it's a bunch of counties, about 2.5 million people live there. And then the sort of inner diagram here, I guess, see if my cursor is showing, that's Allegheny County. And then within the middle of the county is the city of Pittsburgh. And then we take a transect across that county. And this, again, is the population demographics. Again, the fraction of people of color in that sort of same area. So if you look at a cross section through that, you can see that the pollutants are not uniformly distributed, and then the people of color are not necessarily uniformly distributed. This is looking at, race, ethnicity, but you could do this for economics or education attainment. I mean, there are many different demographic variables that you could think about, and we'll look at a bunch of those here. And so it's these sort of correlations of these two quantities that gives rise to environmental injustice. So what if you put this together? So you take a high spatial resolution PM2.5 map, and this was work that was done as part of this EPA-supported center that we had called CASIS, and it was published in KIM, and you take this with the demographic data that I just showed, and you look at the exposures by different demographic groups, and that's what's shown here is the PM2.5 fine particulate matter exposure difference between different demographic groups, and 0 is the sort of population weighted average for the entire country. And so if you look across the country, whites are on average a bit less exposed than the national population weighted mean, and whereas other demographic groups are more exposed. And this represents about a 10 to 20% higher exposure for these different demographic groups. So this is the exposure disparity, and this is, say, these different demographic groups are being exposed to environmental pollutants. So I'm talking a lot about fine particulate matter, and I guess I should have defined it. These are small suspended particles in the atmosphere. Every breath you take, you're inhaling, tens to hundreds of thousands of these particles, and they cause about 100,000 premature deaths in the United States each year, and they're one of the criteria pollutants that's heavily regulated by EPA. So we're going to focus on this pollutant and a number of other criteria pollutants in the talk today. So what's creating these sort of disparities? There's lots of different things that are causing this segregation, I should say. If either the population was homogeneous across the country, or if air pollution concentrations were uniform across the country, we wouldn't have these sort of environmental injustices. So what's creating? There are a lot of different factors that are creating, say, demographic segregation, and some of these, are not, not things that we should be proud of. And so this slide is titled, racist policies contributed to demographic segregation. And so everybody knows about sort of redlining, which is something that arose out of the federal government starting in the 1930s, where they were ranking areas. The federal government was ranking areas about giving loans, by hazard values, with red being more hazardous. And so basically they were rating areas with higher minority populations as hazardous, meaning that they were not going to be able to get loans. And so this obviously moving forward had an impact on where people lived and created segregation in our society. And essentially the underlying belief, a change in social or racial occupancy generally leads to instability and a reduction in home values. And so that's what they were worried about. That was the prevailing view that related to redlining. So that would be one example of what I would term as an intentionally racist policy, though I don't know if that was how they intended it at the time, but it certainly was the effect. Another example in terms of where people live are things like racial covenants that are often in titles, or were often in titles of people's houses, essentially that you couldn't sell the house to a person of color, and that was prohibited. And so, here's an example from a development in the Seattle area. Said lots or structures shall not be rented, leased, or occupied by persons other than those of the white race, except domestic servants. And if you read, the book Color of Law, it really talks about, these types of challenges. And so these types of policies, which weren't phased out, until say the 70s or late 60s, really had a big influence on distribution of where people lived. Obviously, there are many other factors, and we're not even talking about citing of sources, but it's this segregation, it's these types of things that give a rise to the potential to have this environmental injustice. So what about national trends? And so I'll look a little bit at NO2 data here. So this is another criteria pollutant. And we're going to look at a whole bunch of different cases here, but we're going to look at data for both 2000 and 2010. And so the box whisker plot that's shown here, it shows the distribution across the country of, I can't remember if this is annual average concentrations. But one thing you can see is that, between 2000 and 2010, concentrations across the concentration, or mixing ratio in this case, went down, by, 50% or something like that. And this shows the effectiveness of, our laws and our policies and the National Ambient Air Quality Standards. So the air is getting cleaner, which is a wonderful accomplishment, and we should be very proud of it in the United States. But what we want to do is we want to disaggregate all the different neighborhoods that are in those bars and look at how it changed for different classes of people. So if you look at race ethnicity, and so this was work that was done by Laura Clark that was published about 6 years ago in EHP. So if you look for race ethnicity, so again, we've got two sets of bars here. So we've taken the data and we've spread it into these different categories. So again, the gray bars, the gray box whiskers are for the year 2000, and then the white bars are for the years 2010. And so you can see there's a big difference between the different populations. So Asian non-Hispanic have the highest exposures in both 2000 and 2010, followed by Hispanic any race, Black non-Hispanic, 2 or more races, white, and then American Indian. And so essentially we see the same ordering in 2010. And so even though the air quality is improved, and it's improved for everybody, if you look at the data carefully, the relative differences haven't changed. And so even though our policies are improving our air quality, they're not reducing these exposure disparities between these different demographic groups. So this is just one lens to look at it, race ethnicity. Another one that people often ask about, what about household income? And so this is dividing household income into quintiles. And you can see that there's really not much trend but with household income and exposure disparity of NO2 between these 2 years. And the data look very similar for PM2.5 and other pollutants. It's relatively flat. You can see that it's actually a little bit U-shaped. The lowest income quintile has a bit higher exposure. The highest income actually has the highest exposure. And again, this is often in big cities, say New York City, some of the wealthiest people live in, so that's what that trend is. But if you compare that very, very modest trend, to what we see with race ethnicity, it's very flat. I mean, essentially, you can't explain the trends, say, in race ethnicity by income is essentially what this is showing. And the differences by income are quite small. How about educational attainment? Again, the story looks very similar. It looks very similar to household income. Again, there's not much trend with educational attainment, certainly much smaller than race ethnicity. And then you can look at it with age. I mean, so there's a variety of different ways you can slice and dice the data. But if you look at exposure disparities in the United States, really race ethnicity is really the most prominent variable that doesn't explain it, but that's where there's by far the largest trends. All these other potential explanatory reasons, things like income, have a much less influence on the data and things like that. So if we're thinking about reducing exposure disparities, really need to think about race ethnicity. And this again goes back to what I was showing earlier with things around redlining and things like that, and how that, among many other policies, set up some of these challenges that we have today about these exposure disparities. So what about other pollutants? I'll just show a little bit about other pollutants. And so this is the gap between non-white and white, so people of color and white. So the purplish means that the people of color are exposed to higher pollutant levels than the national average, versus the inverse if it's sort of that peach color. And so you can see for different pollutants, NO2, they're the biggest exposure disparities. It's a primary pollutant. And you can see that they're throughout the country. And about 3/4 of the states, or 3/4 of the population lives in these states. It's useful to think about it on a state perspective because a lot of air quality policies get implemented at the state level. So you can see California for NO2, a number of states in the Midwest, in the East, but then, those are the most purple, but then there are many other states. Ozone or regional pollutant, you can see that there's no disparities, at least at the state average level. If you look at individual cities and things like that near roadways, There may be some influence, but say thinking about a national, at the state level. And then you can see that the ones for PM 2.5, which is a blend of primary and secondary pollutant, is somewhere in between ozone where there's none and the primary pollutant NO2. But again, for PM 2.5, there's a lot of states where there's people of color are more highly exposed than on average. So again, there's clear evidence of sort of widespread, broad environmental injustice. I'm going to skip this one. This again is looking through all the different criteria pollutants, and I think the story is basically the same. And if you go look at the literature, a literature review, I mean, we've done one of these recently. There's more than 300 papers that talk about, exposure disparities, and about 90% of them, have findings that are very consistent with what I'm showing here, which is based on some of these national exposure models that we built, which are described in this paper that we published in Environmental Health Perspectives in 2021. So clearly there's a challenge. I don't think it's a big surprise. I mean, environmental justice is something that came out of the civil rights movement in the 70s and 80s, and it certainly gained awareness, and definitely in the last few years, it's really gained a lot of sort of prominence. So this is a bit of the introduction, sort of setting up the challenge and what do we want to sort of think about. So there's a problem clearly, but let's think a little bit about solutions. And, this is an interdisciplinary seminar, and and so there's many sort of facets, policy, law, economics, regulatory structures, and of course, science and engineering. And, if you're thinking about pollution exposures, this is sort of the, causative chain where we've got emissions that lead to atmospheric concentrations, that lead to exposures, kind of the environment right around where you are, intake, what actually goes into your lungs, dose, what gets absorbed into your body, which ultimately corresponds to have health effects. And so looking across this entire chain and, really to reduce those health effects, ultimately that's why we control sources and emissions. And so linking, what types of sources are driving these disparities, I think are very important to understand. While we understand the magnitude of the disparities, we have much less understanding of what the sources are. And then that's key to think about policies. And so in the next part of the talk, we'll get into the kind of meat of it. And really, we'll be focused on two questions. What are the sources that create these existing exposure disparities in PM 2.5? And so spending a little bit of time, we've worked on this problem. And this is like the first step, which sources, and then you can think about, the types of policy tools that you might use to control that source. So the second question that I'm going to address a little bit towards the end of the talk is how do existing regulatory approaches impact exposure disparities? And so in the United States, of course, we've been regulating air quality for 50 years, even more than 50 years in some parts of the country. As I showed with that NO2 data, or you look at the EPA trends report, there's been enormous progress improving air quality, but how have they impacted exposure disparities? We already saw with NO2, the regulations were reducing exposures, but they weren't really reducing exposure disparities by race, ethnicity, and so that's part of it. And then here we'll talk a little bit about what alternative regulatory approaches might be used that might be more effective how we do now. And we'll look a little bit at the Biden administration Justice 40 initiative. So hopefully we can get through all these different topics here in the next half an hour or so. So what exposures are driving these PM 2.5 exposure disparities? And so we're going to look at just two sources, and these are important urban sources. And so there's traffic, and traffic is certainly a super well-recognized source. Motor vehicles, very heavily regulated. There's been a whole series of federal regulations over the last 50 years to reduce emissions, but of course there's an enormous number of cars and people driving around. So looking at the role of traffic, which is one that we know is driving environmental injustice, and sort of quantifying that. But then the other one we're going to look at is cooking emissions. And so these are from restaurants and homes and things like that. And this is just a few locations in the United States is regulated, but is it also important to find particulate matter in urban areas that hasn't been, as I said, regulated. It certainly hasn't had the sort of level of emission controls sort of put on it, and look at what the contribution of cooking is. And as I go through this part, I'll talk a little bit about how you build these exposure maps and some of this stuff, some of the detail behind some of those plots that I showed earlier. So the first thing I want to talk just is how do you go about developing these high resolution maps of source resolved PM2.5 exposure? And so we use an empirical approach. And so we go out and do sampling. We do both mobile and fixed sampling. We have to do with relatively sophisticated instruments that can tell us enough about these small suspended particles that let us say something about the source. And we've done this in different urban areas and throughout the country, and we'll talk about that, using an instrument called the high resolution aerosol mass spectrometer. We do something called positive matrix factorization, which is a source apportionment analysis technique that you can do on the mass spectra. And this can take the composition information that you have on the particles and separate those particles into different source categories. So we do that. And then we do something called land use regression modeling, which is a way to build these highly spatially resolved models, very widely used in the exposure community. And then we can take those models and build concentration maps and predict exposures to PM2.5 for these different sources at the census tract, census block group level. So really at very high spatial resolution across the entire country. And then we can integrate those estimates with health data. So we do a lot of epidemiology analysis on these types of data. But for this talk, I'll be talking about the work we've done around environmental justice. And so mobile monitoring, it's a really powerful tool to bring sophisticated instruments and use them, say, all over a city or all over the country relatively efficiently, much better than fixed site. And this is work that we've been doing with Google. This is one of these Google Street View cars that's been equipped with air quality sensors. And this is the van that I used to have at Carnegie Mellon, where we'd put much more sophisticated instrumentation like the aerosol mass spectrometer. So this is what the instrumentation is. It's about a $500,000 instrument. You can load it up in the back of a van, which is shown here on the right. You can drive around with it. And the key with this instrument is it gives you information on the chemical composition of the non-refractory component of fine particulate matter, which you can put it into a source apportionment model, such as positive matrix factorization, to divide that particulate matter into sources. So we have one of these instruments and we can drive around. We've spent months and months driving around different cities with it to understand the spatial patterns of the composition and sources of PM2.5. And then we use this modeling approach to scale that up across the entire country. So we systematically sample cities. This is just one example. This is Pittsburgh. So you can see where the rivers are coming together. So Three Rivers Stadium or Heinz Field is right here. This is downtown. And you can see these are just some of the tracks. I mean, this is, here's 1 kilometer. So this is kind of a 6 kilometer by 5 kilometer kind of area. And we sample a broader region than this. But you can see what we do is we go drive every single street or many streets here to characterize the composition of the aerosol across this. And we do this many, many, many times to get a representative value for that location that we can use as a measure of the exposure. And we've done this sort of driving in 3 different cities across the country, in Pittsburgh, in Oakland, California, in Baltimore, Maryland. And the purpose of this sampling is to really get this sort of intra-urban area or variation in composition and sources that we can then use to extrapolate across the country. Here's what a sample drive. We would drive around, in a big urban park next to the Carnegie Mellon campus. Concentrations are quite low. And then we go out into the city. So we get on a big highway through Pittsburgh. Pittsburgh doesn't really have big highways, but this is probably 3 lanes in each direction, which is big as the interstates are in Pittsburgh. And here we go through a tunnel called the Squirrel Hill Tunnel. And you can see there's a little blip in PM levels as we go through the tunnel. And this is associated with the tailpipe emissions. I would imagine if we went through this tunnel in the 1960s, the blip would have been much bigger, but the fact that it's so small reflects the fact of the effectiveness of emission controls. And we went through this tunnel during rush hour, and there were standstill moments and things like that. But then we start driving around other parts of the city and we see lots of signal, concentrations not just in single digits of micrograms per meter cubed, but concentrations up to 100 micrograms per meter cubed. And many of those high concentration events occur around restaurants, pubs serving burgers, Chinese restaurant, things like that as we drive around. and you find these plumes. You could also do this around industrial facilities, but this is just an example. And then when we wrap up the drive, 3 or 4 hours later, we drive back through this big urban park and get the background concentration, which relative to all the other changes has been relatively small. So the great thing with this mobile sampling is you can go take this instrument and go systematically sample different parts of the city to understand what we call sources or modifiable factors and how they're influencing exposures and concentrations in a way that you could never do with fixed sites. And this is just an example. Here's looking at a top view of these different sorts of areas. And some of those high concentrations was occurring just downwind of a restaurant area. So there are a number of restaurants on the street called South Highland in Pittsburgh. The wind was blowing this direction, and you can see there are plumes, downwind. You can see downwind through this neighborhood of concentrations up to 100 micrograms per meter cubed, which is quite high. The daily standard for PM 2.5 is 35, and the annual standard is 12. So we're seeing concentrations, at least in this plume, that are 10 times higher than the standard. But you can see around it, upwind of this restaurant area, there's not these types of concentrations. And so with this mobile sampling, we can, get this kind of data, which we can then translate and model to develop these exposure maps. So this would be a data set that we have. So we have a bunch of fixed points. There's these dots around the map, all these fixed points. And then in these target cities, we have this really high spatial resolution data that we've developed. So this is the data set. It's about 100 and some odd points, very strategically sampled across a bunch of different environments that we can use to try to build one of these land use regression models. So that's what's going in to build the model. What are these land use regression models? You can certainly use machine learning techniques. There's a lot of different math that you can use. Our data set for this sort of source resolved PM is not that large, so we have to use a relatively simple approach, which is just a simple multilinear regression. You do actually a supervised regression with a lot of different predictor variables to identify which ones are most important. But essentially you have this linear combination of these different predictor variables, things like traffic, industrial facilities, and say green space. And you have a regression, and your regression fitting the model, you determine these coefficients beta, and then you can use that to predict the concentrations. So you fit the model with measured concentrations to determine your beta, and then you can run the model backwards, put in these covariates, land use covariates from different places, and then predict what the concentrations are throughout space. So this, again, is a very common approach, and there's a whole variety of these covariates that you can use. So these predictor variables are covariates. There's some of our air quality data that we have shown. Basically, you grid the city. This is a 200 meter by 200 meter grid. You grid up the city, and for each grid cell, you can draw basically buffer zones around it and look at the number of restaurants, traffic in it, population, green space, all sorts of different variables that you can drive that have an influence on ambient outdoor particle concentrations, and you can use those when you fit your model. So we have a whole big number. There's a couple hundred different potential predictor variables, like traffic, inverse distance to the nearest road, different classifications of road, population, land use type, imperviousness of the surface, emissions data, elevation, restaurant count, et cetera, et cetera. And then these are for different buffer zones and things like that. So you do a supervised linear regression where you systematically run each of these variables through the model, figure out which ones are most statistically significant, explain the most variance in the data, and select those, and then stop selecting variables once you've sort of explained as much as you can with a set of predictor variables. This is a very standard approach for modeling, and allows you to build very high spatial resolution models and of air quality. Of course, it's an empirical model. It shows you what's today. It's not like a chemical transport model that you can look at future scenarios. So this is what a model might look like. This is the cooking model for cooking PM 2.5. So it selected these variables: impervious land use surface area, which is a urbanicity variable, restaurant count, commercial land use area, and it actually selected restaurant count on two different areas. And the model explains about 66% of the variability of the data. And this is based on predictions against holdout data that you don't use to fit the model. So it isn't goodness of fit, it's this holdout prediction. And there's a variety of ways that you can do this kind of model evaluation. So we've looked at it a lot of different ways with, sort of k-fold validation, defined spatial holdout, which looks more at the ability of the model to extrapolate and things like that, and, evaluate what the performance of the model. It's not perfect. I'm not going to argue that it's perfect, but there is certainly some predictive ability, and there don't seem to be systematic biases when we look across these different areas. So it provides us a tool to start thinking about either, the health effects, is we can link this to health data or to demographic data and think about environmental injustice. So what do the predictions look like? So we fit these models with this data that we've collected, and then we can predict exposures to, say, traffic PM 2.5. So this is tailpipe PM. So it's the combination of black carbon plus primary organic aerosols that are emitted. And these are the predictions of our model at, I think this is at the census block level. Certainly you can see, one of the predictor variables for traffic obviously is, road volume, and you can see the interstate network, but you can see each of the, cities are sort of lit up as well. And then if you blow up within the city, there's a lot of sort of fine structure within the city as well. And so we're comparing this to, say, the total PM 2.5 here, and you can see traffic is a much smaller fraction. It's only contributing, say, 10% of the total PM 2.5 mass. This is primary traffic emissions. So traffic, of course, contributes a lot of precursors that make secondary aerosol, but this is just primary. And then for total PM, you can see that, the traffic is a small fraction, say for 10%, but it's also much more spatially heterogeneous compared to the total PM, which is a lot of secondary components, so it's a much more sort of regional pollutant. So again, you can look at this, for a particular, again, in the Pittsburgh metro area. So again, this is that MSA that we looked at earlier. This is Allegheny County. This is the city of Pittsburgh. We have a transect that goes through just to kind of visualize the data. And you can see that, most of the PM 2.5 exposure is what we call background or other. And the sources that we're looking here are only contributing, 10 to 20% of the total PM 2.5 exposure, say, within the city. And that's what's sort of emphasized. You can see the structure of the data here, and compared to the independently modeled PM 2.5 mass. They're not perfectly correlated, but they certainly are, they're somewhat correlated. So these are the data that we've developed, these source resolved estimates of PM 2.5 at high spatial resolution. You can see as you look across the city, you can see this, all the structure in the data that you wouldn't see, say, in a chemical transport model simulation, which has much, much lower spatial resolution. So we're going to go back to that original figure that I showed. This was one that I started out with that showed these exposure disparities. These are for white. The national average is 0. So it's relative to the national average. So the average white person's a bit lower, black person's is higher, Asian, Hispanic, and people of color. And so we saw this before with the total PM 2.5 map, and now we want to break these bars down into these colors. And this is what we just did. So we took these maps that I was just showing you and broke those down. And you can see, the contribution of the exposure disparities. The contribution of cooking is in yellow. The traffic, organic plus BC, that's like the combination of traffic. And then other is really the final piece. And so it's striking if you compare back to the previous slide, right, where other was contributing, say, 80% of the total exposure. If you look at the exposure disparities, others only contributing about a third of the exposure disparities. And so cooking and traffic, which are relatively minor contributors to the total exposure, are actually really driving the exposure disparities. And this isn't too big of a surprise because of, they're spatially distributed sort of in interesting ways. So the fact that traffic contributes about a third of the overall exposure disparities by rate ethnicity. That is I wouldn't say well known, but not surprising. I mean, certainly there have been other studies that have looked at exposure disparities associated with traffic. But the surprising thing from our studies that cooking is almost as important. It contributes about a third as well. And so that's a source that hasn't been looked at very much. And it actually, if other studies confirm this result, it certainly would suggest that, controlling cooking emissions might be a way to effectively and efficiently reduce exposure disparities pretty significantly in urban environments. There's certainly technology that exists to control cooking emissions, that's been deployed somewhat. So it's a little bit sort of low-hanging fruit. And so this is kind of, one of the set of conclusions we see from this is that these, relatively minor sources in terms of, driving total exposure in urban areas are really driving the exposure disparity. So I'm going to shift gears now and talk just for a few minutes about, regulatory approaches. And so we have some understanding of sources, which I think is really important, but then you need to think about a policy framework. How are you going to go about controlling these sources? And we, as I said, we have a very well-established sort of regulatory framework through the Clean Air Act and its subsequent amendments, that serve the country really well in the sense that our air quality is so much better than it was 50 or 60 years ago. But, as we saw before, say with the NO2 data that I showed, it's not clear that it's really addressing this issue of disparate exposures and exposure disparities. So we're going to look a little bit about these sort of regulatory approaches. So the work I'm going to highlight here is from a couple recent papers that we had. So one was in PNAS about a year ago. Summer came out in August of 2022, looking at location-specific strategies, sort of different regulatory approaches. And then the other paper I'm going to highlight here is a paper that just came out this summer in Science, a policy forum piece that specifically looked at the Biden administration Justice 40 initiative and the potential effectiveness of that. And so hopefully this will give you a sense of potential path forwards from a regulatory approach. And so the first thing is, as all of us are aware, there's been real substantial awareness of the environmental justice challenges and racial injustice generally in society across many different dimensions. But if we think about environmental justice, it's certainly much more on the radar. And the Biden administration, input, initiative, which they call Justice 40, to try to address that sort of historic environmental injustice. And, it's committed to delivering 40% of the overall benefits of federal climate, clean energy, affordable and sustainable housing, clean water, and other investments to disadvantaged communities. And so they have defined disadvantaged communities. And the hope is if we implement or we invest, say things like from the Inflation Reduction Act along these lines, following the guidelines in Justice 40, that maybe we'll be able to, really substantially reduce some of the environmental injustice that we see in the data today and has existed for decades and things like that. So we're interested in evaluating, say, the effectiveness of this approach on exposure disparities to outdoor air pollutants. Of course, I want to say, Justice 40 is trying to solve many, it's bigger than just air pollution. It wasn't designed to solve the air pollution problem. That was one sort of angle. It was designed to do more than that. And so we'll just be looking at sort of one potential facet. So we're going to look at a little bit of data. So these are some predictions that we did with a chemical transport model, looking forward, looking across the United States, looking at population weighted average exposure disparities from different communities. And so and it's looking out 10 and 20 years. And the emission reductions that we put in the model were what we call business as usual. So if you look back historically since the Clean Air Act amendments sort of were put into place in the 1970s, air pollution emissions have decreased at a few percent per year. And we just continue on that trajectory with the assumption that essentially we continue this sort of business as usual and national ambient air quality standard approach. This is looking at a subset of the population, which are defined as disadvantaged communities. And these are defined by the Biden administration, and they're articulated in a tool called the Climate and Economic Justice Screening Tool, CEJST, kind of rolls off your tongue. And what you can see for these communities, or for the total population is shown in orange, you can see as we reduce emissions, the air pollution levels go down. You can see that the disadvantaged communities have that's the light blue line, has a higher exposure than the average population. And then the non-disadvantaged communities have a lower. And then you add, the average of those two is the orange line. And I think it's significant here, and not surprising given the data that we looked at earlier for NO2, you can see that the lines are not converging, right? And they essentially stay the same distance apart. And that indicates that while the air quality is becoming better for everybody, still the disadvantaged communities are going to, even in 20 years, after another big round of reductions in pollution concentrations, are still going to be exposed to higher concentrations than the population as a whole or the non-disadvantaged communities. And so what I would argue there is the kind of business as usual approach of NAAQS, which has caused such dramatic improvements of air quality and will in the future, as indicated by this chart, isn't addressing this problem of exposure disparities. So if we look at a couple of other variables by race and ethnicity, remember at the beginning of the talk when I was looking at the data, race ethnicity was where the biggest exposure disparities. You can see that they're much bigger than the Biden administration defined disadvantaged communities on the left-hand panel by race ethnicity in the middle. But the conclusion is basically the same. There's a little bit of crossing lines here, within different ethnic groups. But again, the people of color, all those different lines are well above the population-weighted total population average, and with the whites being below that. And so this, again, is this exposure disparity. And so the business as usual approach isn't going to solve the problem. And we haven't seen it solve it in the back. We looked sort of historically with the NO2 data, and you look back at ambient monitor data, it's clear that it hasn't worked in the past. And this is just saying it's not going to work in the future. And the same thing around income, but you can see the income curves are super tight. And that's because income, there's not a lot of disparity by income as we saw in the data before. And that's what the model is predicting going forward. So this is setting us up, and what it's arguing is the business as usual, kind of the NAAQS-based strategy that we've used to drive emission controls and reductions in emissions is going to improve our air quality, which is super valuable, but our current approach isn't going to get at these exposure disparities, which suggests we need new approaches to tackle the problem. And you could think about the Biden administration Justice 40 as being a potential new approach to target emission reductions to potentially try to shake this up and to try to reduce the difference, reduce the spread between these curves. So is there a better approach? And so we've evaluated, this is what we did in that PNAS paper. And so we evaluated the effectiveness of some different sort of policy approaches. And we looked at a number, but I'm going to only highlight sort of two of them here. And so the first one is just a NAAQS-like approach. And this, again, is modeling work, looking at reductions in concentration disparity between the most exposed group and the national average, or maybe between the most and the least. I can't remember, but the trends would be the same. And that's what's shown here on the y-axis. On the x-axis is cumulative emission reductions per year. And the total emissions are on the order of 30 megatons. And so what this is showing is, and obviously there's this sort of one-to-one line. If we get and we eliminate all the emissions, there's obviously going to be no concentration disparity, but that's going to be impossible to do, right? I mean, how do you have human activity? And what the model is showing here is essentially, we're basically following the one-to-one line. And so what I would argue is the NAAQS-based approach, business as usual, is really inefficient. We have to get a lot of emission reductions, a third of emissions to starting to have an effect on reducing the exposure disparities. And so the question is there a better way? And so we've looked at a number of different ways. And one way that's super effective is if you choose the right locations, you actually can have very, very little emission reductions and actually eliminate exposure disparities. And we identify these locations with an optimization algorithm. And I think a bunch of work needs to go around sort of how would you codify this into policy, but it's a different approach to thinking about targeting emission reductions. And this gives us hope. I mean, this is obviously the best case. It's a model. It's, an optimization. The real world isn't going to work like the model. It's not going to be as efficient as the optimization algorithm. But we can reduce, 1 or 2% of the emissions in the optimization algorithm and basically eliminate exposure disparities. And that suggests that there's really are very effective paths forward, but we need to think about regulatory strategies that try to target these locations as opposed to the kind of more generic kind of NAAQS-based regulatory strategies. And you can think about the Biden administration Justice 40 approach being one of those types of strategies where they've identified all these disadvantaged communities across the country. And what happens if we target those emission reductions in the disadvantaged communities identified by the Biden administration Justice 40? And so essentially the bottom line here is these sort of location targeted emission reductions are super highly effective at reducing these exposure disparities. You can see that essentially almost none, and the concentration disparities go basically down to 0. So then it comes down to, does Justice 40 identify the right locations? And so we'll step through this graph and look at some Justice 40 sort of approaches. But first we want to talk about kind of where we are right now. So this is current, this is kind of the, today simulation using the model, the chemical transport model, is showing, the predicted exposure disparities for disadvantaged communities, which are real. For people of color, about twice as big as for the Justice 40 defined disadvantaged communities. And then if you look for, say, the most exposed race ethnicity, the both most exposed group, they're the largest. And so this is looking, what those exposure disparities look like today. And then this here is a relative exposure disparity, the disadvantaged groups are about 7%, the people of color are about 15%, and the most exposed is about 20% more exposed relative to the national average. So that's current. And this is very consistent with like the data that we've been looking at around PM 2.5. So the next is we're going to look at the business as usual. So this is that NAAQS-like scenario that we looked at. And what you can see is, there is, just as we looked at the previous figures, so you can see there's some reduction in disadvantaged community, there's some reduction in people of color, and there's some reduction by race ethnicity, but it's modest, and this is 20 years out, so it's actually pretty substantial additional emission reductions. And if you look at the relative disparities, it actually goes up, so it actually becomes cleaner on average than it does for, say, people of color or for the most exposed racial ethnic group. So here, you're cleaning everything up, but you're actually cleaning up these disadvantaged communities, people of color, are most exposed race ethnicities slower than you are for the general population. So the relative exposure disparities go up, which seems counter to what we want to achieve. And so this is business as usual. We already knew it wasn't going to go work, but that's what it's shown here. So let's look at the Biden administration Justice 40 approach. And so we're targeting the emission reductions. So everywhere in the country is going business as usual, but then we target some additional emission reductions in the Justice 40 areas. And we have sort of a target emission reduction in the Justice 40 is kind of this intermediate blue, and then we have like an aggressive one, which is twice as much emission reduction as this other one in that. The details are in the science paper. We have sort of a targeted and then a super targeted. And what you can see here actually is with the Justice 40 initiative, it's better than business as usual. You can see here it goes from, I'm looking at the upper graph, hopefully people can see my cursor. You can see that it goes down, but it certainly isn't eliminating in 20 years, which corresponds to a pretty substantial emission reduction, exposure disparities for either people of color or the most exposed race ethnicity. It definitely is reducing or eliminating it for the disadvantaged communities. And this isn't a surprise because that's where the targeted reductions that's where the reductions are targeted. This is the Justice 40 identified disadvantaged communities. And you can see again with the relative exposure, for the most exposed race ethnicity, for the Justice 40, those targeted emissions, it's actually going to increase the relative exposure again. So we would argue that at least in the context of air quality or PM 2.5, which is obviously just one measure of air quality, but a very important one, the Justice 40 initiative may not achieve the ends that we might hope in terms of eliminating environmental injustice with these pollutants. But maybe some refinement of it, because what we showed previously, location-based approaches would work. It's just that Justice 40 doesn't seem to identify the right areas. And I'd be happy to talk about that in the Q&A. So let me wrap up here. So I guess I've really just been talking about stuff in the UX context, which is an important context, but I think it's really important not to, to think also globally. So we've been talking about the United States. So this is a figure from Josh Apte. It's a distribution of PM 2.5, outdoor PM 2.5 exposure. And so low exposures are down here, high exposures are off to the right. See, the United States is here in blue. Our air quality compared to the rest of the world is actually pretty incredible. And it really speaks to the effectiveness of a regulatory strategy. So we've been sort of looking at the exposure disparities in this little bump which is the cleanest kind of bump of the countries sort of specifically shown here. But many other countries, Western Europe is higher, but then you look at places like China, India, Nigeria, Pakistan, Bangladesh. I mean, their exposures are, a factor of 10 higher than they are in the US. So, the issues that we talk about in the US, which are sort of contained within this blue hump, are sort of shown in spade when we think about it globally. So I think it's really important that we don't just think of environmental injustice as a national problem, but we all have the right to breathe clean air. So just to summarize this right at the end, I mean, just to emphasize the title of the talk, we don't all breathe the same air. I think that's obvious. The past is the present. I mean, things like redlining, racial covenants and titles or whatever created, the world that we live in today, and it's driving, it's underlying, these inequities that we see. And then the final point is, these inequities will not just eliminate themselves. I mean, we see this, we've got very effective air quality regulation in the United States. It's really cleaned up our air, but those regulations have not eliminated the exposure disparities. And looking into the future, it doesn't look like they're going to eliminate it in the future unless we really essentially eliminate all emissions, which isn't very realistic. So I think there's a lot of opportunity, with these location-based approaches to potentially have a lot of benefits. So I just want to end with thanking my collaborators. So I'm the one here talking, but really it's the people on this slide that have really done, all this sort of incredible work. And I just really want to highlight a few people. So Julian Marshall is someone I've known and worked with for many years. He's a faculty member at University of Washington. He's been working in environmental justice and air pollution for many years. He co-directed this EPA center with me. Some of these slides were from Julian. He's really been an incredible partner. And I just want to highlight a couple of students. Yuzhou Wang, who's a student at University of Washington that did a lot of the sort of regulatory work that I showed, that PNAS paper, as well as the science paper that just came out. She's done a tremendous work. And then Provat Seha, as a postdoc, has worked with me for many years. He drove a lot of this kind of source resolve stuff. And so just giving them a shout out. And then at the bottom, I have our funders, a lot of funding from EPA, some work funding from the National Science Foundation has supported this, the Allegheny County Health Department, which is the local health department around Pittsburgh, and then the Heinz endowments. So anyway, so thank you for your attention. I took a little more time than I'd hoped, but I'd be more than happy to take questions. So I don't know how
please.
that.
Well, people can go ahead and raise their hand, and I can call on them just to organize the Q&A session. Or if you can let me know in the chat you have a question, or you can type it out, and I'll read it out loud. Evans, I see you're unmuted. Is that to ask a question?
Can you hear me, Casey?
Yes.
My question was, thanks, Dr. Robinson. Very enlightening presentation. My question was regarding the method or the section that you were trying to explain how your results of source contribution. How did you link your results of source contribution to your exposure disparities? You explained the method in 4 sections, if I remember: measurements, and then PMF model, and then land use, and then another part, which was, I forgot, yes, exactly. So yes, a very clear picture of the method that you have been conducting in the project. My question was, how did you technically link it to your exposure disparities? Maybe you mentioned that, or I was wondering if you could go a little bit on it. Thanks.
Yeah, I mean, the link to exposure disparities, I mean, this is kind of the chain, the modeling chain, where we get data, it could be through mobile sampling or some other, you get this spatially distributed data. And so that's sort of well-established sort of techniques. Our approach is to apply it more like the way the exposure community is using it, to get the kind of data distributed in sort of covariate space you need to build these models. The PMF is a very well-established approach to do source apportionment. to basically decompose the mass spectra that you measure with the aerosol mass spectrometer into source categories. And then this land use regression modeling is a way to then both first fit the data and then use those fits to predict out in space. And so you end up with these spatial maps of concentration by source. And so, I mean, these are just some examples. You could think about the color scale is, to say the concentration, I don't know exactly which pollutant this example is, but say it's, traffic emissions. You can see they're high here in the city, they're lower around the city. And then in some of these, rural areas, they're quite low. So you have these very high spatial resolution maps of pollutant concentrations that you predict using the data you've collected, the analysis of the data, and this land use regression modeling. And then what you do to predict disparities, you basically just combine this with demographic data, right? So it's not a difficult way to do. It's like a convolution type calculation where you combine this with this data in space to basically sum up what different populations are, the average exposures. It's like a population weighted average, but you're doing it for sort of subsets of the population. So combining this map of pollution that you built with the land use regression model using these techniques that I just described, combined with the population, it's a very simple calculation to do if you have the spatially resolved data for both, that then you can sum up to give you, say, the population weighted average exposure disparity for Black people relative to the national average. So hopefully that at least gives you kind of a low Earth orbit view. If you look up the papers, there's lots of references here. They get into the equations and the sort of nitty gritty of how the mechanics of doing it, but hopefully that gives you sort of a conceptual idea.
Perfect. Thank you. I appreciate it.
And of course, there's uncertainty in the models. I mean, there are all these types of challenges, but when you think about rolling them up and you're rolling them up at a national level, are those uncertainties, are they biased towards certain demographic groups? And so you can look at these types of questions, and if they're not biased towards particular groups, by summing up across the country, you actually can, the certainties sort of fall away a little bit. Around any particular road, the uncertainties may be larger, but as long as it's not biased around one of those, you can get some advantages there. And so I'm not going to say this is perfect. I mean, there's Achilles heels and all these types of analysis, but it's one approach. This is one approach to try to tackle the problem. Kind of a bottom-up approach using measured data.
Yeah. I have used these techniques in my studies previously, but the thing is, this is the, I guess, only available approach to tackle these problems. So yes, there are some uncertainties, but the good thing is they're not biased. And that was perfect. Thank you for your answer. Appreciate it.
Well, I mean, we can argue whether or not they're biased. I would argue they're not biased by these demographic groups. And this is an argument, say, that, has been used in the epidemiology literature as well, around doing those types of studies. And there are other approaches. I mean, you can use a chemical transport model to do this. I mean, the challenge is it's going to be very difficult to get the kind of spatial resolution that you want in urban areas. But that's another approach. And people have done that as well. And I haven't seen it done on a source basis. Anyway, I see Russ has got his hand up.
Yeah. Russ, you can go ahead.
Hey, nice job as usual, Alan. And I couldn't agree more that modeling that's going to be tough. These disparities can be at the scale of 100 meters or less, and good luck getting WRF to work at that level. So okay, so a specific question. We're working in this area, as are lots of people, and it's of course a wonderful tool you have for identifying different kinds of sources. But a more general question is, if you want to solve the issue, I wonder if you could talk about involving the community activists, and the enforcement people. I think both of these are really important if you're not just going to measure the pollutants, but solve the problem, as you seem to be focusing on. So what have you got to say about those two partners?
No, I think they're key. I mean, if you actually look, the paper in Science, there are people from some EJ groups that are co-authors on the paper, and they provided sort of very sort of valuable perspectives. And so I think that's key. And definitely, you know, academics parachuting in and, you know, collecting their data for some paper. I mean, that's happened for decades and things like that. So I think engagement with the community is very important. I think often, Russ, I mean, right now we're thinking about sort of at a systemic, at a national level. And so, you know, there are some national groups. Certainly in my own research, say in the Pittsburgh area, we would work very closely with community groups and, you know, using that not only to help direct our research, but have them participate in the research. And I think that really helps build buy-in and trust. And so I think that's so important. But it's very hard to do, say, on a national scale. You know, obviously regulators as well. I mean, we've certainly shared this, you know, with EPA and others, and they're very interested in our work and you know, engaging them as well. I mean, regulators, I mean, I guess it's, yeah, I don't know. I think the community groups is the bigger one. I think there's so much distrust out there. I mean, right now in the society, there's so much distrust. I mean, you think about, you know, oh, I don't need to have my kids go to university because it's not valuable. I mean, these recent polls, I mean, it's just crazy. And you like to think we're honest brokers, but we're definitely not perceived that way. And so really building that trust is critically important. So it's something that we've done. I think a lot more needs to happen. I think the trends in research, there's definitely a lot more community-based research that's happening where you're doing it in partnership with communities, which I think is really important. And I think that's, you know, what's going to have to go forward because A, to trust your results, and B, you know, this is a seminar for an academic audience, but, you know, something like this to a community group, I mean, people are just like rolling on the floor. You know, what's this, you know, kind of guy with the aluminum foil hat talked about. But I think that's so important. And I think really our job in academics, you know, certainly now that I'm at Colorado State as a land grant school in particular, is really that community engagement is a real tenet of what we're doing. It's one of the reasons I moved here. Very excited about that kind of aspect. But I think it's critically important. So I completely agree with you, Russ.
Okay.
And creating tools that they can use, right? So I think there's a big need to you know, democratize and, you know, not only the tools, but the data and the models. We've worked very hard to make models more accessible. And we have community groups using models, putting them on, you know, they're not using WRF, but they're using, you know, much simpler and maybe not as good as WRF, but they are accessible. So there's lots of things that I think we need to do to empower everybody.
So we are at time, but Ross does have a question. Alan, did you have somewhere to be right this moment?
I've got a few more minutes and I got to march across campus to the anatomy and zoology building.
Okay, one more question. You got it, Ross.
Okay, thanks for a great talk. I had two questions related to what's on the screen here, cooking and traffic. I think the easy one will be first for traffic and then the hard one for cooking. My traffic question is, do you have a breakup of, you know, trucks versus cars? Because I think the community activists are going to want to clean the exhaust, you know, out of their through the neighborhood. So if you had truck versus cars, that would be great. My second question related to cooking. So I grew up in Baltimore. I know Baltimore very well. And you know, I'm basing my cooking comment on the history in India. You know, it's very hard to get people to change cooking habits in their homes. I know that's not what you're talking about, but you know, in inner cities, restaurants that vent to the environment, it smells good and it kind of brings business in. So do you have any experience successfully overcoming the cooking emissions in an urban environment that you could share with us? So two questions.
Yeah, I think those are great. I mean, so at this point, I mean, I think we could get a gas and diesel kind of estimate. I don't think we could refine it below that. I mean, obviously in the air quality community, gas and diesel split is, you know, there are knife fights, lots of dead bodies strewn around, you know, trying to sort out that particular question. I think we could make a stab at it, but you know, that's I think an open research question. But I agree with you that you know, from a community group perspective, definitely in a regulatory perspective, you would want to nail that down. I think the cooking is different. I mean, certainly in New York City and LA, there's been some, you know, efforts to put some controls on cooking, and I could send you some of that work, but I agree it's really challenging, you know, because I mean, I can also send you a lot of articles, you know, when you know, there was rumblings about controlling cooking, you know, down, it's like, what are you going to control our barbecue or something like that? You know, these are sort of blog posts and stuff. So it's not, you know, this is what the data show. Whether or not how you could do it politically is really challenging. And then this also brings up this other question about, which component of PM 2.5 or components are causing sort of the health effects, and is cooking really one of those that are, that contributes to mass? Right now we have a mass-based standard, which is assuming essentially ecotoxicity of all the different components. Is cooking really the component that's causing the problem? And we've looked at that, we've done epi studies on that, and cooking doesn't appear, traffic appears more associated. But again, that's another one of these sort of holy grails, is trying to better understand the sort of PM health effects. But I won't disagree. I mean, cooking, I think, is a challenge. I mean, we all love that, that smell, and I think that's, how we've evolved. Another example of a pollutant that falls in that category is things like ammonia emissions from agriculture. I mean, that's sort of an important part of the sort of PM story, not of the exposure disparities, but if we look at the absolute burden. And again, historically has never been regulated, again, because it's getting into the agricultural community. And, that's could be considered a third rail. And so it may be that cooking is a third rail. The technologies exist. I guess I would like to think that, there would be a path forward about how to address it, certainly at the restaurant level with, basically catalysts inside your hoods and things like that. But I won't disagree that I think it's challenging. And I think where we are now in the United States, levels are quite low, and we've sort of, hammered on the coal-fired power plants and diesel trucks a lot. We can hammer on them a bit more. But, if we really look at, say, the WHO, the 5 microgram per meter cube standard, I mean, we're only going to get to 5 if we really start, and not that that's what the EPA standard is, but they're discussing going down between 9 and 10 is what the administrator said. I mean, we're going to be getting into some of these sources that aren't somebody else. Ultimately, it's our activities as humans which are causing the sources. We always like to say industry or somebody else, but they're just responding to our needs. And so there's a lot of interesting, we could have a couple of beers, Ross, talking about that, but I don't have the sort of magic bullet. I guess I would say I have lots of awareness of the challenges. I could certainly point you to some articles where they are putting in some of the controls, but I can also point you to a lot of hate mail, not to me, but, blog posts and TV coverage about when, this was floated and people going pretty berserk, which is kind of the norm for, our society these days.
Well, thank you so much for that great answer. And if you do have a chance to send anything, maybe you could send it to Kazi, Russ, and myself. Kazi's the most important person to be sure it gets to others who might be interested if you had anything.
Yeah,
Thanks again.
I'll point you to a couple of things. I've actually got a version of this talk where I actually go into that issue in a bit more sort of detail. One that was just about cooking, and there's a lot of great sort of quotes and things like that. I'm not saying it's going to give you much help, Ross, but it definitely gives you a few good slides of outrage about controlling cooking.
Alan, I'll remind you, because I was also going to ask if we could share your slides, if you're all right with that.
I think so. I think basically everything's published. I guess there are a couple slides that aren't published, but we're just about to, so maybe those I would not want to share. I don't want to get in trouble with the copyright police, but it's almost published. So we just got reviews back, and looks like we're going to get it, accepted in just really shortly. But everything else has been published.
Okay, perfect. But we can omit whatever isn't currently published. But you have to go. I don't want to keep you longer. We're already past our time. But thank you so much for coming to talk to us about this today, and thank you for everyone for showing up and being so engaged. This was a great talk. We are going to continue our talks next week. We have same time, same place, online. That's all. Have a great day, everybody.
Thanks, everybody. Always fun to talk about our work. Bye.
Bye. Thanks.
Bye-bye.
Bye-bye.